continuing on with our thermochemistry, we are now going to look at some of the problems that you might get in chemistry. So we've got problem-solving steps. We've actually got two types of problems that you're going to get. One is experimental. You're going to get a heat of reaction that you have to calculate experimentally. And one is theoretical, where you'll be calculating the enthalpy of reaction. The reason why I've called one enthalpy because it's mostly theoretical in terms of moles. The other one is heat of reaction because that's basically what you're going to measure. So for the heat of reaction experimental, you're looking at changing temperatures, positive or negative, and you calculate the amount of heat that's released or absorbed by combining the temperature change with the known heat capacity, for example, water. And then you calculate the number of moles which actually reacted, and then you calculate the amount of heat that's released per mole of reactant. That gives you the actual heat of reaction or the enthalpy of the reaction experimentally. Theoretically, you have a slightly different process. Normally you'd write out the complete chemical equations, including the states. You might even write sub-equations to include the formation of each compound in those equations. You then include any heats of reactions that you already know, for example, the heats of formation, the standard enthalpy of formation. And you might also have a list of bond energies, for example, if you're trying to work that out. And then you would calculate the enthalpy of the final reaction just simply by comparing the enthalpy of the products to those of the reactants. So the total energy or the total enthalpy of reaction is always the sum of the products minus the sum of the reactants, or sum of the enthalpy of the products minus sum of the reactants. Some examples: the heat of reaction. This one's barium hydroxide, which is similar to, say, sodium hydroxide. They're making up a solution, so this is a dissolution reaction, it's a heat of solution. Most of the time you have a small amount of one thing and a large amount of another. In this case we've actually got a fairly large amount of the solution, 100 mils, which is placed in a beaker, and nitric acid is added to it. So this is a particular reaction between barium hydroxide and nitric acid. The heat that's given off was measured, and it was a change between 20 and 23, so it's about 2.5 degrees. And total volume of the mixture is actually 300 because you've got to include the 100 mils of the first solution and 200 mils of the second solution. Assuming that your density is still 1 gram per mil, then you can look at the mass of that 300 mil as being 300 grams. We are making an assumption here that during the reaction you have no change in density, and yet nitric acid is actually slightly more dense than water, so this perhaps might not be a good assumption. We also use the specific heat capacity of water. This is actually quite a reasonable assumption because most of your solution is water, but it is still an assumption. The chemical equation shows that we've got 4,284 joules of heat that's produced. Now we need to work out how much that is in terms of moles. So we had 0.0404 moles of barium hydroxide. Your nitric acid was in slight excess. You can see that it's a 2-to-1 ratio. So using that and then divide by the 0.04 moles, you end up with 1.06 times 10 to the 5 joules per mole. So about 100 kilojoules per mole for that particular reaction. An example for the heat of solution is something like ammonium chloride, which we tried to do in class. It dissolves in water and the solution becomes colder, so it's an endothermic reaction. And sodium hydroxide, when it dissolves in water, heats the solution up, so it's an exothermic. So we can calculate the enthalpy of solution using standard enthalpies of formation. In this case, we've got sodium chloride, and in its standard state, sodium is a solid, and chlorine is a gas. And this is the energy of formation of sodium chloride as a solid. And then we look at how much the enthalpy of formation of producing it as an aqueous solution. In this case, we're looking at that solid and that gas turning into aqueous, and that's the standard enthalpy of formation for the aqueous solution. The overall reaction, you'll notice that this cancels out with this, and the overall reaction is basically the solid sodium chloride turning into aqueous sodium chloride. The enthalpy of that reaction is simply the product minus the reactant. And we know what the product is with this, and the reactant, we know it was that. So we can work out product minus reactant will give us 4 kilojoules per mole. So this is actually a slightly endothermic reaction. So it goes slightly cooler. The heat of neutralization is generally used for acids and bases. And the standard enthalpy of reaction is when you use 1 mole of water. So we've got sodium hydroxide, hydrochloric acid produces sodium chloride and water. So we used sodium chloride before. In this case, we're actually just using water. Because all strong acids and bases produce water, they end up actually all having relatively similar standard enthalpy changes of neutralization of about 57 kilojoules per mole, or minus 57 kilojoules per mole. The main reaction in this case is actually the water. So the enthalpy of formation for water from its constituents, which is hydrogen gas and oxygen gas, is 285.8 kilojoules per mole. That's exothermic. To actually produce hydroxide ion, which would be from, again, hydrogen gas and oxygen gas, in aqueous state, the enthalpy of formation would be 230. Of course, for the hydrogen ion, it's 0. That's actually a standard statement for this one. When we look at the actual enthalpy of the reaction, products minus reactants, then we have that minus that, and you end up with minus 56 kilojoules per mole, which is very close to that standard enthalpy change of neutralization. And most strong acids and bases will have that. Weak acids will have slightly less because not all of the acid dissociates. But we're not getting to that until we get to kinetics. The heat of combustion is when a fuel is burnt in oxygen, always in oxygen, and when it's complete combustion, it always produces carbon dioxide and water. That's always exothermic, so your delta H, your enthalpy change, is always negative. But sometimes you get the heats of combustion listed as positive values. You always remember that the enthalpies for a combustion reaction are negative. And the amount of energy that's produced is directly proportional to the methane burnt. How does this actually look? Well, you have your methane burner under here, or it could be ethanol burner or methanol or butane, anything. And it's used to heat up a certain amount of water. You can calculate how much water, how much energy the water is absorbed by the change in temperature. You have a calorimeter, which may or may not heat up. Copper is a very good heat transfer, so it might be good to have a copper beaker if you don't mind leaving charred, sooty marks on the bottom. And you end up with a result where you can work out the energy produced per gram of fuel and convert that into kilojoules per mole. So the process, fuel is burnt, energy is produced, heats up the water, you measure the temperature change, compare that to the amount of fuel that you use to make that temperature change, and then calculate your molar heat combustion. Some of these things that we've been talking about, all these heats of reactions, can actually be combined in something called Hess's law. And this is a conservation of energy thing. It kind of says that it doesn't matter what way you go through a reaction, the enthalpy changes are always the same. So this can be considered in terms of potential energy and, say, climbing up a mountain. Climb up a mountain, if you climb straight up, it's still going to take the same, by the time you get to the top, you're going to have the same potential energy as if you went up in a circular path and took a little bit longer on a smaller gradient. So this is an example of it, is oxidation of nitrogen to produce nitrogen dioxide. So nitrogen, oxygen to produce nitrogen dioxide. It's an endothermic reaction, so 68 kilojoules for this 1 mole of gas. It can be carried out in 2 steps, and the enthalpy changes are different. So you can see the first change, we're producing nitrous oxide, which was one of the examples in the previous videos, and it gives you an enthalpy change there. And that nitrous oxide is then reacted with excess oxygen to produce nitrogen dioxide. And here is an exothermic reaction. So we started off with endothermic reaction, exothermic reaction. The net reaction is just the sum of those 2 enthalpies, which gives you 68 kilojoules. So the overall reaction is endothermic. The sum of these 2 steps gives the net or overall reaction. And that's basically what Hess's law states. You can sum up the individual reactions to get the overall reaction, which is why, and the diagrams that you might use are simply like this. So nitrogen oxide goes up into that 2-step reaction, and then you have a 1-step reaction. There's your 2-step there, but the reaction you actually want is just this one to that one. So this is another example of a different reaction. This is with hydrogen fluoride, and it's using the bond energy type description. So again, Hess's law still applies. You're breaking some bonds, and you can break them in this form and then reform them to produce, I think it's HF is what you're looking at, hydrogen fluoride. But the energy that's used to break those single bonds, the HH and the FF, and then have a HF and another HF, is the same as if you went directly from the reactants through to your products. So, just to review, these are the ways that you would use problem solving to solve these equations. Experimentally, from data that you're given, or from data you collect, or theoretically by using these chemical equations. And remember to use Hess's law so that if you have any of these sub-equations, when you get to the final equation, you can look at the enthalpy change by either adding up the individual equations or looking at the enthalpy of the products compared to those